Hello everyone, you're all very welcome to this presentation. I'm Mark Flanagan from University College Dublin, UCD in Ireland, and my presentation today will be about reconfigurable intelligent surfaces. And in particular, I want to talk about the optimization of the achievable rate for MIMO systems assisted by reconfigurable intelligent surfaces. And this is a joint work with my former postdoc, Dr. Nemanja Stepan-Parovic from Paris-Saclay University in France, my colleague Linan Tran from UCD, and also Professor Marco Di Renzo, who's also from Paris-Saclay University. So to begin, I'd just like to give an overview of this seminar. I'm going to start by giving an overview of the technology of reconfigurable intelligent surfaces and what we can do with this technology. And then I'm going to move into the more technical part, which is on the optimization of the achievable rate. I'm going to cover three cases: the point-to-point MIMO case, the case of multi-user MIMO, and the case of MIMO discrete signaling. Okay, so I'll start with just a brief overview of ORS technology. So the idea here is to create a programmable or smart radio environment. And the easiest way to think about this is to think about, well, what is our traditional approach to wireless? So usually what we do is we think about optimizing the transmitter and receiver operations. So for example, the hardware, the signal processing, the implementation, and we think about the channel or radio environment as being somehow stochastic and something we can't control. The idea of a smart radio environment or programmable radio environment is to significantly depart in a disruptive way from this kind of way of thinking about things. The idea is that we want to control the interaction of the waves in the surrounding environment with the surrounding environment itself at the electromagnetic level. And the reconfigurable intelligent surface is a way of providing this kind of control. So the idea is that the wave impinging on the RAS, for example, the diagram here, we can control the interaction and in fact the reflection properties of this RAS. And this way we can achieve some kind of channel engineering. The channel is actually reconfigurable through adapting the RAS, and indeed the channel can adapt, or the reflection properties of the RAS can actually adapt and track, for example, where the users are in the environment and how we want to reflect. So this is a very different kind of system to this traditional system. Other advantages of these reconfigurable surfaces would be that they can be manufactured at low cost and that they're nearly passive. In other words, the RAS will require some small energy to be configured to set the reflection properties, but then in its normal operation, it is actually passive. It's simply doing some reflection. And for this reason, it's a very green technology. One of the reasons I show it in green here, it's a sustainable technology for 6G. And in contrast to its competitor, in other words, active relaying, you don't need any power amplifiers or other complex hardware. Okay, so there are many applications of RAS. So one of them would be, for example, in enhancing the transmitter. So if you use your RAS as part of the transmitter, such as, for example, is used in a holographic MIMO application, then you can effectively design a low-cost transmitter which is capable of creating any kind of transmit waveform in a very, very flexible way. The second one, which I'll talk about today, is link enhancement. So in other words, making the link stronger, increasing SNR capacity and so forth. But there are many others, such as, for example, increasing the physical air security, doing interference management, multiple access, things like localization, sensing the environment, and even integrated communications and sensing. So it's a very flexible technology. There are many use cases for this. So today I'd like to just, since I'm going to move on to the technical part, I want to introduce the communication model that we're going to adopt for this particular talk. So it's a basic phase shift model. It's a simplistic model for the RAS operation, but quite good in practice. So if we take this simple SISO system, for example, you can see that we've assumed there's no direct links. This is somehow blocked, and our communication is via the RAS. And the way we model the RAS is that it has these reflection coefficients, these θ1 to θn RAS. So we've n RAS as the number of these reflecting elements, and each of them is simple phase shifts. So is represented by a unit magnitude complex number. So we have a vector of channel coefficients from the transmit antenna towards the RAS elements, and we have another vector of channel coefficients from the RAS elements towards the receiver. If we look at the SNR that we can gain on this indirect channel, if you like, and then what happens is it goes as the mean square value of the cascaded channel gain. This is the overall cascaded channel gain, which is of course a sum of all the channel gains that you get on all the different reflection paths. And what we can do is by designing or optimizing, if you like, these RAS reflection coefficients, these θ values, we can actually align the phases to achieve constructive interference of the receiver. And what happens is that the SNR goes as proportional to the square of the number of RAS elements, which is of course a very promising result. So this kind of phase shift model is quite good for mathematical tractability, and it's the one that I'll use in this talk today. I'll just mention as well that there are more advanced models, such as, for example, in practice, we tend to have discrete phase shifts, not continuous ones. We tend to have also an amplitude phase dependence. so that there's, excuse me, so there's the phase shift you can achieve, the amplitude gain, which we're assuming is 1 here. There's no power loss in this particular model, but there should actually be an amplitude loss, which is very easy to model actually. But of course, this amplitude loss tends to, or this power loss, if you like, depends on the phase angle of the RS, and that dependence can be incorporated into the model. You can also have mutual coupling or correlation between the RS elements, which is also something we can model, and up to fully electromagnetic compliant models. So while these advanced models will not be, let's say, directly addressed in this talk, it is possible to actually generalize or extend the methods that I'm going to talk about today towards those models without too much difficulty. Okay, so I'd like to talk about the first piece of work that we've done in the group on this topic, which is the rate optimization for the point-to-point MIMO case. So let's look at the system model for this. So we have a MIMO system, in other words, a multi-antenna transmitter, a multi-antenna receiver. We imagine that the direct path is somehow weak, in other words, blocked by some obstacle, and we're communicating via a weak direct path, but also an indirect path expressed through these channel matrices H1, H2, and these distances, etc. I guess the most important thing, this model here that we're giving here, the geometry of the setup is really tailored to an outdoor environment. And I would just mention here, the important parameter here is this DRIS, which is the distance of the RS from this transmit antenna plane. And of course, that goes from 0 to, let's say, 500 meters in terms of being close to the transmitter, close to the receiver. So let's have a look at the overall channel matrix we achieve in this MIMO system. It can be decomposed into a sum of 2 parts. There's a direct path and indirect path. The direct link, if you like, also has a line of sight and a non-line of sight component. But more importantly, if you look at the indirect link to the RIS, you'll see actually that involves a cascade of some channels, where the inner matrix here consists of the part for the RIS. So this is the optimization we want to perform. If we also consider the path losses, it's worth looking at this. The path loss in the indirect link is actually it's more the path of the indirect link is more attenuated than the path of the direct link. And the reason for this, by the way, is that we have this product distance model, which is fitted to the RS in the far field. So because of this product distance, what happens is that the attenuation of the signal is actually the path loss, if you like, is very high on the indirect link as compared to the direct link, which is a more simple model. And the upshot of this is to balance this high path loss in the indirect link, you actually need to adopt a sufficiently large number of RS elements. In other words, this NRS parameter needs to be sufficiently high, so you'll actually achieve some gain out of adopting the RS technology. Okay, so let's get down to the details of the rate optimization problem. The achievable rate of the MIMO system can be expressed in this way. We want to optimize it, and we want to optimize this rate over some parameters. First of all, the phase shift vector, in other words, the vector of phase shifts of the RS, and also the covariance matrix of the transmit signal. We have a power constraint, a transmit power constraint, and also a unit modulus constraint on the RS elements. Okay, so let me explain how we actually solve this problem. We use something called the projected gradient method. So the idea is, starting with the feasible point, we take some step in the direction of the gradient, and then because we may not land at a feasible point, we project that then back into the feasible set, and we continue iterating this process. So that's the idea. What we do this is we do this process sequentially on the phase shifts of the RAS, and then we do it on the covariance matrix. Okay, so this is the step here in the direction of the gradient, followed by projection. This is P theta, is a projection onto theta, and followed by projection, step and projection onto Q. And we iterate this process until we reach convergence. What is the advantage of this? Well, the main advantage of using this projected gradient method is that we are doing a vector update. So we're actually updating the unknowns, or the quantities we want to optimize in parallel. And this is particularly important in this RS application because the number of RS elements, and thus the number of unknowns, is actually very large in general, possibly in the order of hundreds of thousands, and therefore it's important to be able to optimize in parallel. This contrasts with the existing approach of alternating optimization, which sequentially optimizes each phase shift value and then the covariance matrix, which is of course much slower to converge. So another advantage of using this particular form is that we can obtain all of the gradients and projections that we need can be expressed in very nice compact closed form expressions, which is, for example, I've illustrated here for the gradient respect to the ORS elements and the covariance matrix are expressed in a simple way. Also, the convergence of the projected gradient method can actually be proved. If the step size is small enough, then we can prove that we converge. Now, we cannot prove that we converge to a global optimum, but of course, that is not something that can be proved for any of these iterative algorithms that attempt to solve such a complex problem. I'll also mention as well the projection is actually particularly suited to this scenario as well, in the sense that we have a unit modulus constraint for all of these ORS element values, and therefore projecting onto unit modulus constraint is particularly simple. Okay, we also introduced something here called free space path loss ratio. And the idea here is we want to really pose and answer a fundamental question, which is, should we actually add an ORS to the system? Is it beneficial to add this technology? And we can answer this in a rough way by considering what's called free space path loss ratio. This is a new item that we've defined. And what we do is really we're comparing the path loss and the indirect link to the path loss and the direct link. And if we do this on the basis of a SISO system analysis, we can come up with a nice formula, simple formula, which you can see that the path loss, this indirect to direct path loss, which we call T, it depends on certain things like the geometry of the scenario. And there's these distances we defined. Also the wavelength of operation, the number of ORS elements, and also this parameter E, which, if you like, summarizes the relevant statistical properties of the channel. So by looking at this parameter T, if T is larger than 1, then of course the direct link is stronger. So we're going to get some, our main gain is coming from the direct link, and it's not really perhaps worth putting in the ORS technology due to its cost. Whereas if the T is much less than 1, then of course we're getting a lot of gain from the ORS, and it's actually worth putting in that technology. And we found that even though we derived this formula for the SISO system analysis, it actually is quite useful as a rule of thumb for the MIMO case. Okay, if we look at this free space path loss ratio, we can see some interesting things as we vary the distance of the ORS. So as it moves from the transmitter region on the left over to the receiver region on the right, we find that in the center of this region, of course, T is very large, and it's simply not worth deploying ORS technology, regardless of any other overheads. Whereas if it's in the vicinity of the transmitter or the vicinity of the receiver, we find that T becomes quite small, certainly smaller than 1. And in that case, we are actually getting some benefit, some significant benefit from using the ORS. Interestingly, if you don't use this ratio and you reason simply on the total distance or the total path length, if you like, in meters, then what happens is you get some misleading results. You would find, for example, the total length of the path is actually increasing as you move the ORS towards the receiver. And so it looks like maybe perhaps it's a bad place to put it, but we're seeing from this path loss ratio, it is actually giving us a lot of gain in that region. Okay, this, by the way, this experiment is done for the case of a 2 gigahertz operation, where we have, we're assuming half wavelength spacing between the ORS elements. This is to reduce the channel correlation. And what happens is for a 225 ORS square formation of ORS elements, which corresponds to about 1 meter squared, then this is the behavior we're seeing. So the upshot of this is the best ORS placement is, as has been found in other works, it is to place the ORS close to the transmitter or close to the receiver. Okay, looking at some of the convergence properties of our algorithm then, if we look at the classical way of doing this, which is the alternating optimization method, because of the very large number of ORS elements and therefore the very large number of iterations you need, we're seeing here that the convergence is actually quite slow. And note that the iteration number here is on a log scale on the x-axis. So in contrast to this green curve, we're finding that with the projected gradient method, the convergence is very, very fast. Again, it's less than 10 iterations, as you can see. So apart from this much faster convergence with the projected gradient method, we can also see that the gain is there with using the ORS. For example, we're getting 6 bits per second per hertz with the direct link only, that is without the ORS, and this is boosted to over 9 bits per second per hertz using the ORS. This is, of course, when the ORS is close to the transmitter. If we place the ORS close to the receiver, we get a very similar story. The same kind of conclusions apply. Okay, some other experiments that are of interest here are when we increase the number of ORS elements. So first of all, on the left, what I show is when we increase the number of ORS elements, and what we're doing is we're keeping the frequency fixed, and therefore we're keeping half wavelength spacing between the ORS elements. So as the number of ORS elements increases, what happens is the physical size of the ORS is actually increasing. And in this case, what happens is the achievable rate tends to increase, and we get a logarithmic increase or approximately logarithmic increase, as we might expect. If we, however, look on the right-hand side, what we're doing in this experiment is we're increasing the frequency of operation. And what we're doing here, I guess, is there are two things that happen when we increase the frequency of operation. And by the way, I'm keeping the fixed, we're keeping this physical size of the ORS fixed in this particular picture. So as we increase the frequency of operation, two things happen. Number one, with increasing frequency, the path loss on the indirect link becomes smaller. In fact, it gets smaller on the direct link as well, but the effect is more pronounced, much more pronounced on the indirect link. Okay, the second thing that happens is as we increase the frequency and we keep the spacing between adjacent RS elements at half wavelength, what happens is that we can we decrease the spacing between the RS elements, and therefore we can pack more RS elements into the same physical area, and that of course increases the gain we obtain in the rate. So these two effects tend to balance each other out, quite surprisingly, if you like. As we increase the frequency, these two contending effects tend to somehow cancel each other, and the achievable rate is held approximately constant as we move upwards. Interestingly as well, if you look at the gain, or sorry, if you look at the rate contribution from the direct link, that is actually decreasing, becoming more and more marginal as the frequency increases. And once we reach 5 or 6 gigahertz, actually it becomes almost zero, and almost all of the gain is coming from the use of the RS. In other words, the indirect link. Okay, if we then look at similar experiments in the indoor environment, we find similar conclusions, except the gain is actually a little bit better. So we find here, for example, looking at the AO, again, it takes a very long time to converge over 100 iterations, whereas our PGM algorithm converges rather rapidly. And again, if you look at the direct link only, we're only getting 1 bits per second per hertz, which is just about tripled through the use of the RAS. So it's certainly very useful to deploy the RAS in that particular geometry. Okay, then we'll have a look at the, okay, let's have a look at the computation complexity and runtime of the algorithm. So we see some interesting things here, again, in favor of the use of the PGM. If we look at so what we're looking here is with the direct link present, we're increasing the number of RAS elements, and we find that accordingly, the per iteration complexity of the projected gradient method is actually increasing, as we might expect. However, to counterbalance this, it turns out that the number of iterations you need, that is this IPGM, is actually decreasing as we increase the number of RAS elements. So taken together, the number of iterations, the complexity per iteration is increasing, but the number of iterations is decreasing, and overall we get that these somehow just about counterbalance each other, and the complexity is not really increasing very dramatically, at least for the case when the RAS elements, the number of RAS elements is increasing in this case. If you look at, in contrast, the alternating optimization, what happens is the complexity is actually increasing quite dramatically, and certainly much higher than that of the PGM. If we take the case where the direct link is blocked, it's even more favorable to the PGM. In fact, in that case, you have a very small constant number of iterations for the PGM. So even though that complexity is increasing, it's increasing very slowly, and certainly very favorable comparison with the complexity of AO. If we turn to the idea of looking at the runtime rather than just counting iterations, then we find the comparison is even more stark. If you look at the alternating optimization, the time required to convergence is much orders of magnitude higher than what we need for the convergence of the projected gradient to a near optimal achievable rate. Okay, so just to talk then about the, let's say, extension of this approach to the rate optimization for the multi-user case. If we like the multi-user case, we have a MIMO broadcast channel. So in this configuration, what we have is a system model where we have a base station communicating with a weak direct link with a sequence of users in some region. So we have an RAS which is assisting in this communication, and we'll imagine that the users are all uniformly distributed in this gray shaded slab here, which is corresponding to a group of mobile users. So each user will have a direct link plus a link which is assisted by the RAS, and each user's received signal will contain the useful signal to that user plus interference, multi-user interference from the other users. Okay, so to deal with this problem, we want to formulate the achievable sum rate of this MIMO broadcast channel. This result is well known, and the result looks like this. This is the achievable rate which can be achieved through dirty paper coding. We want to maximize this quantity. We want to maximize respect to the RAS phase shifts, which have unit magnitude, and also the covariance matrices of the different corresponding to different users, which we have a power constraint on these. So to solve this problem, this is a very difficult problem. So what we do is we actually convert this using a well-known duality result into the achievable sum rate for the dual multiple access channel, which results in a more compact objective function. And then we again have these covariance matrices, which are constrained through a power constraint, and we have the RAS reflection coefficients, which are constrained through a sequence of unit modulus constraints. So just to summarize, without going into some of the technical details here, just summarize the approach. We actually use an alternating optimization approach to solve this problem. You can see on the left, this is the algorithm which is optimizing the covariance matrices. And then the algorithm 2 on the right, we embed that algorithm into the alternating optimization, which is the parent algorithm, if you like. So what we do is we repeat the sequence of operations where we optimize the covariance matrices, and then for each RAS element, we will compute the optimal phase shift, and then this is repeated until convergence. So just to give you a snapshot of the results, the main point here is if we look at the gain you can achieve through the direct link only, and we look at the gain we can achieve through the RAS link, we are outperforming both of these significantly through combining the direct and RAS links. We're getting much higher, a higher gain, a higher achievable sum rate through those through the combined channel. Again, assuming that we optimize the covariance matrices and optimize the RAS phase shifts jointly in a good way. And again, we're seeing how the convergence properties are shown here. The convergence is within 200 iterations, and you're also seeing that the gain is actually increasing according to the number of users in the system. Okay, and then finally, I'm going to talk a little bit about the case of optimization of this sum rate in the case of discrete signaling at the transmitter. Again, we're going to go back to the single user case for this optimization. So here the system model is a little bit in the first topic that I talked about. This setup is very much similar to before, and again we've got the RAS at some distance from the transmit plane. But the difference here is we're going to consider a more realistic constellation. Instead of assuming Gaussian signaling to get the maximum achievable sum rate, we're going to take a more realistic model where we've got some, let's say, QAM constellation, and we're going to use some kind of precoder here before the transmission. So the thing about this is that there's a very large number of possible transmit vectors. There's a discrete set, but a very large number of possible transmit vectors. So how do we deal with optimizing the sum rate in this case? Well, instead of the capacity, we now need to move to the mutual information. So if we look at the mutual information measure, we see that it's a rather complex function, and certainly there's a lot of summations over this large number of possible transmit vectors. So what we do to simplify this is we use a surrogate metric, which is the cutoff rate. The cutoff rate is a approximation to the mutual information, which has a much simpler form, as you can see in the expression. And the nice thing is this forms a lower bound in the MI, the mutual information, so it's suitable as a surrogate metric for optimization. And there are two things here, I guess. First of all, the proximity of this lower bound, so how good is it as a lower bound on the mutual information, but also how good is, in other words, is it possible to, is it true that if we optimize the cutoff rate, we are also near optimizing the mutual information, even if the bound is not that tight? Okay, so first of all, I'll just talk about the problem formulation and solution here. If we look at the expression of the cutoff rate as our objective, we have a constraint in the power of the transmitter, in other words, in the precoding matrix, and also in the RAS phase shifts. And what we attack this problem, the way we attack this problem is through the projected gradient method. Again, in a similar way to before, we follow the gradient of the phase shifts, and then we project each one, and then we follow the gradient of the precoding matrix and project onto the feasible set. So the nice thing about this approach is we can obtain closed forms gradients and closed form projections. So I've shown here what these formulas look like. They're nice and compact. They can be used in a low complexity manner to obtain the gradients and also to obtain the projections. The unit modulus projections are again very natural and very simple, and the projection of the precoding matrix is also relatively compact. Okay, so just to go through a few of the results on the optimization of the cutoff rate and the mutual information. If we take the left-hand side, we can see the convergence here over iterations, relatively quick convergence of the cutoff rate and the corresponding mutual information. So if we look at the cutoff rate using the PGM approach, that's this curve here in the blue, and we're seeing that it's reaching a high value after a small number of iterations. And we're also seeing that is also, if you look at the corresponding mutual information curve, and we see that's actually following the same trend as indeed pushed higher than the cutoff rate. So it does point to the idea that the cutoff rate is a good surrogate metric for actually optimizing the mutual information. Just to see whether this is actually a good optimum that we're reaching, we implemented a different method, which is successive convex approximation approach. This is perhaps not a suitable method in terms of its complexity. It's got a higher complexity, but we do the test just to see do we get a similar optimum. We do indeed get similar values at the optimum for the SCA method, which is a quite different approach. So this points to the some evidence, let's say, for the local optimality and possibly even the global optimality of this approach. If we then look at the what we get in terms of cutoff rate and mutual information when there is no RAS and it's a direct link only, you'll see it again that's quite depressed compared to the advantage we can achieve from the RAS. If we then look at what happens when we have a realistic constellation, so for example, if we look at QPSK constellation and we use let's suppose we use a Gaussian-based optimization. In other words, do we need to use this cutoff rate-based optimization, or is the Gaussian-based approach going to be fine? If we use the Gaussian approach for the case of QPSK, we see we achieve something like 2 bits per channel use. But of course, if we use the cutoff rate-based optimization, this is vastly improved to just about 3.7 bits per channel use in that case. So in other words, for the constrained constellation, certainly like QPSK is highly important to get the gains to actually use not the Gaussian approximation, but this particular cutoff rate optimization. If we then take the case of 16 QAM, which is again closer to the Gaussian approximation, we find that in that case we get what we're getting in the red curve is from the cutoff rate-based optimization. The red curve is for the Gaussian-based optimization, but we can increase this still quite significantly. The gain is smaller in the 16 QAM case, but it's still appreciable gain, and thus there is still a reason to use the cutoff rate metric in this case as a surrogate for the mutual information. And in fact, you'll see that when we do that, we get extremely close to this green curve, which is the actual achievable rate with Gaussian signaling. Okay. So just a few conclusions then on this talk. We've provided some efficient algorithmic solutions for optimizing the achievable rate for RAS-aided MIMO systems. And we provide optimization solutions for the single-user MIMO case. We've extended to the multi-user MIMO case. And we also consider the case of discrete signaling at the transmitter. In particular, we've highlighted the applicability of the projected gradient method approach for solving optimization problems in the space. It's a particular suitability in the sense that it's a vector optimization. We're doing parallel processing in terms of the optimization. We can often get closed form expressions of the gradient. We have provable convergence, a lot of very attractive properties for this particular setting. And we've shown that results show promising performance gains in indoor and especially in outdoor and especially indoor environments where we achieve very high gains. So there's a lot of work still to do in this area. We need to look at more realistic RAS models, more realistic channel models, to consider electromagnetic interactions between the field and the actual RAS, for example. We should look at advanced modulation and also how to use the RAS in more interesting ways, for example, using index modulation to convey information. And also experimental validation. We need to see in practice, can we actually achieve the gains that we're predicting with our simulations? So just to highlight then a couple of other works I don't have time to talk about today, but many of the work in my group going on in the area of reconfigurable intelligent surfaces. And we've looked at many problems, such as, for example, millimeter wave communications and channel capacity optimization for that setting, deploying RAS for secure communications, things like transmit and receive spatial modulation with an RAS, also topics such as channel estimation and corresponding frequency synchronization for RAS-aided OFDM, and also extension of these kind of ideas I've talked about here towards an EM compliant channel model. Okay, so I'm going to leave it there. That's the end of my talk. I'd like to thank the funding bodies who have funded my research over the last couple of years, the Irish Research Council and Science Foundation Ireland. My contact details are up here, so you can use them. I'm very interested to hear any opinions and to answer any questions on this work. So feel free to contact me. So that's the end of my talk. Thanks very much for your attention.